In this video, we'll discuss multiple linear regression in PyTorch. First, we'll discuss multiple linear regression. Then we'll discuss the problem of prediction. And with respect to PyTorch, we'll talk about a custom module using end-to-end modules. In multiple linear regression, we have many variables or features. And for every feature, we have a parameter. We have the bias parameter, and every variable has its own parameter, and that links to the slope. So for x1, we have b1, for x2, we have b2, and so on. It's helpful to plot these points on the Cartesian plane, where x1 is a horizontal axis, and x2 is a vertical axis. The linear regression equation maps them in the horizontal direction. This will generalize to multiple dimensions, but for the rest of this video, we'll consider the two-dimensional case. It's helpful to use a vector or tensor representation to implement multiple linear regression. We have X, which is a 1x(d) matrix. We also have the feature tensor, and these produce a target or dependent variable y via the following equation. So let's do an actual example where the first element of our feature vector or tensor is 1, and the second element is 2, and then a parameter tensor or vector has the first element of 2 and the second element of 3. For the first part of the equation, we multiply the first element of tensor x with the first element of tensor w, and we do the same for the second, and then we add them. In this case, the result is 8. We finally add the bias term, which gives us 9. We're more concerned with the actual shape of the tensor or vector. We're not concerned with the actual operation, but more with the shape of the input and output tensors. The feature tensor or vector can be visualized as a row vector or tensor, and the parameter vector or tensor can be visualized as a column tensor. We also add the bias term, which is a scalar. Performing the operations, we get an individual output. Let's represent it with this pattern. We can also use the following directed graph to represent multiple linear regression. The first set of nodes represent the feature, the edges represent the parameter values, and the final node represents a scalar output. This generalizes to d dimensions as follows. Before we discuss how to use parameters, again let's try some arbitrary values. We'll create two tensors representing the parameter values as follows. We'll create a forward function, and the only difference from our original function is instead of multiplying them, we use the matrix multiply. You can also use a dot product operation in PyTorch. We then create an input tensor, input the function, and the output is a scalar value, and we add the extra dimension via PyTorch requirements. In this case, the result is 9. We can also perform multiple linear regression on multiple samples. We simply use the matrix or tensor X, where every row in the tensor X represents a data sample, as follows. We'll use the color to represent the different samples. Let's see what happens when we replace the vector x with a matrix. We get the following equation. All that happens is the parameter vector performs dot product on every row of the matrix, and then we add a bias. We get an individual output. Then for the second row, we perform the dot product and add the bias, and we get another output. We repeat the process for every row. The result is a tensor y, who has the same number of rows as the matrix x. So let's see how to implement this in PyTorch. We simply have our tensor x. We call the forward function. This implements the following equation, and we get the result. As you can see, we had a tensor with 3 rows and 2 columns, and the result was a tensor and the result was a tensor with 3 rows and 1 column. Now let's discuss custom modules. Nothing has really changed in our linear regression class, except we'll vary these 2 parameters. We'll set the random seed. In this case, we'll create a linear regression object, but in this case, our input features will be 2, and our output features will be 1. This will produce the following equation. The shape will look like this, and 2 will be the number of parameters, and the tensor input size. The output will be 1, corresponding to 1 row for every input. We can view the model parameters, and we also have the bias term. We can input a tensor with 1 row and 2 columns, and we apply we input it to our object, and the result is a 1-dimensional tensor. We can also input a matrix or tensor with multiple rows. We'll use the colors to represent the individual samples. We input it to the object. It applies the operation, and every row of the column tensor corresponds to every row of the input. Let's look at the colors to get the following correspondence. And that's it.